Hi guys, welcome to my YouTube channel. My name is Lendua. I am a student researcher at the Fiji National University and I'm currently on the Bachelor's of Engineering program. Today I will be presenting on my thesis research. You can like and subscribe to support this research. Um, okay, so this presentation will be on my thesis titled Exploring Densified Biomaterials as Alternative Reinforcements. My thesis is supported by the Fiji National University and the Tertiary Scholarships and Loans Board, and it is supervised by Mr. Cecilio Redoblado, and he is a master's graduate and professional engineer graduate from the Auckland University of Technology. Okay, so this presentation will have 5 parts. In the first, we will discuss the objectives of this project. In the second, we will extract useful information from available literature to find the latest trends in research. We will form also our hypothesis from these trends. In the third section, I will present on what investigation processes and methods I will undertake. And following that, we will now turn our focus to the project management of this project and the project timeline. And then I will conclude and give general remarks on general management of the project. Okay, so our objectives. My first objective is to test and compare the characteristic strengths of densified reinforced biomaterial. Okay, and that means I will be testing on tension, compression, and the flexural strengths. And the next, we will investigate the brittleness and ductility of these materials. And following that, we would like to check also if densified biomaterials compensates for the lack of tensile strength of concrete. I will be presenting on that in the following slides. As we all know, concrete has poor tensile qualities. Okay. The next is very important. We will compare the densified biomaterials reinforcement with steel reinforcement. This is to check their strengths because we can expect that densified biomaterials will now have strengths that is similar to steel. Last but not least, we should be able to conclude that densified biomaterials can replace steel. Okay, so let's move on to our objectives, our research strengths. We will check the background of cheap materials already used as reinforcements. Okay, so the first, bamboo is the most commonly used biomaterial that we have found. Okay, and our first finding about natural bamboo reinforcement was that bamboo increased the strength of concrete by 87%. This was based on a study of bamboo reinforced concrete pavements. And next, the ductility increases with reinforcement until a certain ratio. That means materials that were reinforced with bamboo increased in flexibility, or you can say the ductility with the increase in percentage of reinforcement. Okay, so this may be attributed to the natural flexural strength of bamboo and its high tensile strength. Okay, and further, we find out that 2.56% bamboo reinforcement has a similar ductility to 0.72% of steel reinforcement. Okay, lastly, bamboo is cheap and entirely feasible. However, there's one thing left, and that is bamboo reinforced concrete is still not as strong as concrete. Okay, so bamboo reinforced concrete is still not as strong as steel reinforced concrete. Okay, so that is looking at the natural bamboo. But what happens when we densify bamboo? Okay, so densification process is a new thing that has been happening right now, but there is a new breakthrough in the densification of biomaterials, and this breakthrough was uncovered by Mr. Liangbing. In 2018, he published his papers based on the densification processes, which we will see that it increases the stiffness by 11 times. Okay, And also we can see now that the tensile strength of bamboo reaches, densified bamboo reaches 1 gigapascal, that is 1000 MPa. Okay, high strength steel stands have 0.95 GPa. That's supposed to be a GPa right there. So 950. So high strength steel is 950 MPa, and that's even higher than some of the steels that is being used at the moment in the construction industry. Right now in the construction industry, we're using grade 500, grade 300 mild steel. Grade 500 has ultimate strength of 660 MPa, and you can see that the tensile strength over here doubles that. Next, there you see that the bamboo has a flexural strength of 404 MPa. Mild steel has an ultimate strength of 461. You can see that it has come very close to steel, and in Australian standards, this mild steel is now 430 MPa. We find that Liangbing whose method is cheap, sustainable, and scalable. Okay, this is the most important word of this point, and we would like anything that is scalable, because that means that we can easily mass produce densified bamboo using his method. So that's a good sign. Next, I will show you some diagrams of research that was recently published. This diagram is on one publication that was just published recently in 2020, and you can see that this is reinforced concrete short column and reinforced with certain bamboo sizes and one steel. Okay, so you can see over in this diagram that there is one diameter of 12, and then bamboo has different sizes and increase in the percentage. Okay, so that's a 10 by 10, 15 by 15, and 20 by 20. Okay, so the first observation that from this diagram shows that bamboo reinforced columns increased in ductility with the increase in percentage. Okay, so you can see that when the percentage was increasing, so this was a 10 by 10 and that was a 15 by 15, you can see that the graph elongates towards the right. And when it elongates towards the right, that means it is more ductile. So you can see that the 15 by 15 is more ductile than the 10 by 10. Okay, and but it only increases up till a certain percentage, because when you see a 15 by 15 and the 20 by 20, you can see that 20 by 20 goes back a little bit. So the 15 by 15 is still more ductile than the 20 by 20. Therefore, we can conclude that the bamboo reinforced concrete column increases in ductility with increase in percentage, but the next part is only until a certain percentage. Okay, and we can also see in a second point is that bamboo reinforced column is still weaker than steel reinforced columns. You can see that all of this, the 10 by 10, the 15 by 15, and the 20 by 20 still have weaker strength. You can see that the ultimate strength here comes up to 450 MPa, and over here you can see for steel, 12 mm diameter steel, it reaches somewhere around 600. So you can see that even though you increase the percentage of bamboo reinforcement, you will still see that it is still lower than the steel reinforced concrete. Okay, so we can say that the bamboo reinforced columns is still weaker than the steel reinforced columns. Okay, but now through the breakthrough in Liangbing, whose research by looking at densified bamboo, we can see that he has published that bamboo now has double the flexural strength as natural bamboo. So we can expect something that is different from these curves in our research. Okay, so we will take a look now at the flexural behavior according to Liangbing, whose methods of densification and his testing methods. Okay, so we'll start on the left and then we will move on towards the right. You can see this diagram here that this is the densification using this is the testing using the 3-point flexural method, and you can see that the densified bamboo is always on top, and over here on the side you can see that the densified bamboo is also on top. Okay, so the first observation from these diagrams was that bamboo reinforced column increased in ductility with increased in percentage. Oops, sorry, that is finished. We will now move on. Okay, so speaking of flexural strengths of the new densified timber are now twice the strengths of densified bamboo. Okay, I will show you these diagrams. Sorry, that is already there. Okay, so the diagrams clearly show that the strengths of the new densified timber are now twice the strengths of natural bamboo. Okay, so we can see that the strengths over here, this is the natural bamboo right down there, and the natural bamboo down there. So, and the densified bamboo, we can see that there's exactly a twice. The strengths are increased twofold. Okay, so from a flexural strength of 140 MPa, it has increased to 327 MPa for the natural densified inner bamboo, and for the outer bamboo we have a more stronger strength reached, and that is from the 204 MPa to 404. Okay, so what other thing that we also find is that it has a good, nice ductility behavior in as you increase the strength of the stress. Now we'll look at tensile behavior, also according to Liangbing, whose research on densified bamboo. Okay, now the first observation is we can see that the tensile strength is higher than steel. Okay, at 1008 MPa. Okay, so as I've said earlier, that high strength steel stands at 950 MPa, and grade 500 steel that is being used in the industry in Fiji is 660 MPa, and grade 300 steel has an ultimate strength of 420 MPa. Okay, so we can see that the tensile strength of densified outer bamboo is even stronger. Okay, so the next, the second observation we can see, or the observation that we can find over here, that is that outer bamboo is brittle after yield strength. You can see in this graph that after it reaches its ultimate strength, you can see that there is a rapid decrease in strength. Okay, so that just simply means that after it reaches a remarkable strength, it rapidly decreases in strength. This means that bamboo is brittle after it has reached its tensile strength, and that's something that you wouldn't want to see. You will also always want to see a ductile behavior. Okay, and moving over on toward the right, you can see that there's a difference here. The first is you can notice that the strength, the ultimate strength of the inner bamboo is a little less than the outer part of the bamboo, and it reaches a strength of 770 MPa. This is still stronger than the grade 500 steel, and the grade 500 stands at 660. So it's it's already 110 MPa stronger than grade 500 steel. And the good thing from this graph is that you can see that there's little ductility over there. Okay, so there's no ductility over here, and then there's little ductility over there. So you can imagine when you're using both together, you can expect that the ductility will be more. Okay, so moving on, based on these observations from the latest research trends, we will base our hypothesis. And this is going to be governing the whole research project. Our hypothesis is densified biomaterials can replace steel reinforcements. Okay. All right, so let's move on. In our project overview, we will have to prove our hypothesis. So we have to establish some systems in our project. The first thing that we have to do is have a good project management plan. So project planning was part of the first phase, and the reconnaissance. The reconnaissance is we had to scour journals, searching for anything that is relevant to our hypothesis. We also had to read out those journals and do a detailed literature review. And if you want to access this detailed literature review, it's provided for in the link below, and this is the link to our project timeline, which is on at the ResearchGate website. Our second phase was which is divided into two, is firstly the specification of materials and standards, and then acquiring of certain materials and standards. Okay, the first part is where we at. The first part is a specification of these materials, equipments, and standards of testing. Okay, right now we are specifying materials, and after we have specified all our materials, we find that Fiji National University, or our university, although it has opened this new research lab, we still do not have a few of the materials that we need. This is because the topic that we are on is very current, and we will need some materials and equipment for our testings. Okay, and some of the materials that we have in our labs are also old and damaged. Okay, we will need some controlled environments and controlled temperature specification standards, Australian standards. These are all things that need to be bought. Okay, some things that we really need for densification process of timber is not there at all. Okay, but as I've said, the one thing we have in our favor is that FNU has opened a new engineering research center in Samampula, and that would help us in keeping our temperature control, applying our methods in specification standards. Okay, so even though let's get back to our research. Before that, right now COVID-19 has sealed our research lab out to the public, and especially since this outbreak is now growing and growing each day. So we're providing a link below if you want to research. If you want to support this research program, you can follow the link below to our GoFundMe fundraiser, where you can donate any amount you can. This will mean a lot to me and my fellow researchers. Okay, this will mean a lot to me and my fellow researchers, because we need a lot of support in this regard. Okay, moving on. After the materials acquired, we will plan and construct materials. Okay, we will plan and construct our concrete columns specifically to AS3600 specification, and we will assume a typical Fijian climate. For reinforcements, of course, we will be using densified bamboo. We will be using also densified vesi, and also vesi is a Fijian hardwood, and I'll be talking more about that later in the slides. And we also will be using densified Fiji pine to represent softwood. So we will have three types of materials, and one is densified bamboo, because the bamboo is not qualified as timber, and we will have densified hardwood and also densified softwood. Okay. Then we will have the specimen analyzed by a three-legged truth test. So the three-legged truth test plays a huge role in us concluding if our hypothesis is proved or disproved. Okay, so my part will be the numerical analysis. For that, I will be modeling the behavior of our constructed materials on Abacus modeling software. Okay, so we will try to simulate these materials under various loads, and we have chosen 4 testing schemes. The first is the flexural test, the second is the tensile test, and the third is the compressive strength testing. So lastly, we will observe the cracking behavior of concrete. So this is our project overview. You can see this overview better in the next slide. Okay, and this slide shows you the overview of the project more holistically, beginning from the project management and to acquiring to manufacturing, after which it is being tested in the numerical analysis and the experiment analysis and theoretical analysis. If the results are inconclusive, materials will be then again have to be manufactured and retested again until there is a definite conclusion to fully prove or disprove our hypothesis. Okay, so you can also see in on this chart is the assignments of our members, and the numerical analysis, as I've said, will be done by myself, and these are the details of what I will be doing. The experimental analysis, the middle part over there is this part over here. So it will be manned by 5 people. Okay, that's a lot of people will be manning the experimental process. The first one of which will be first is just going to be focusing wholly on the experimental setup. That is Mr. Rendir Moniel Chan's work, and the rest of the group members the rest of the 4 group members will be focusing on their own individual test, and that is the compressive test, the flexural test, tensile test, and the crack control. Okay, which will be done by those members. And over on the top right hand corner, we have the theoretical analysis, which will be done by Mr. Pernil. He'll be using the latest Australian or New Zealand standards, or we will be using both Australia and the New Zealand standards, depending on the availability of our materials. Okay, so to read all the details, you can simply pause the video and then you can move on. So moving on to the numerical analysis, this is my part of work. The numerical analysis will be carried out on Abacus modeling software. Okay, so it will be an 8-step procedure for simulation. And you can see these 8 steps on the right. I've tried to simplify this as much as possible. And these steps can be used for all parameters needed for testing in this project. All tests will also include the flexural, compression, and tensile test that is also going to be tested in the experimental analysis. The reason we will have both as the same is because we want the experimental analysis to confirm the results of the numerical analysis that is being done in the software. Okay, so in addition to this analysis, we also have the crack control. I will explain more on this. So just a brief overview of the 8-step process is the first definitions. Okay, so in this software, before we will simulate, we will have to define the materials, and for this we will be defining all the 4 reinforcement materials. We'll also be defining the concrete, and then the second is we will define the behavior of those concrete, behavior of those individual materials under loads. Okay, and then we will assemble those materials. After we have assembled, we will introduce interaction points between the reinforcement and the and the actual concrete itself, and then we will mesh up the whole diagrams. And meshing up, this is simply dividing the surfaces into grids. This is just to make it easier for us to visualize the color codes. And loading definitions, this is simply telling the software how much amount of load you want to load, how much amount of force you want to load the specimens with. Okay, and you can also tell the software if you want a compression strength, compressive strength, or tensile strength, compressive forces applied, or you want to apply tensile forces or flexural forces, whatever forces that you'd like, you can define it over there. And the seventh is also is just defining the color codes. The color codes usually are from blue to yellow to orange and to red. Obviously, blue is going to be the lower scale of forces, and red is going to be the higher scale of forces. And 8 is the simulation of the material. So we will be applying this to all of our materials. Next is the compressive strength test. Okay, so looking at the compressive strength test, the concrete column that we will be defining in the software will be 1 meter long. As you can see in this diagram on the right, it is going to be 1000 mm long, and the cross-section area will be 250 by 250, and the concrete cover will be 30 and 30. That is why you have a length of cross. You will see that the cover, the reinforcement from the inside is 30 mm from the sides. Okay. Our main goals is to firstly determine the ductility or brittleness of the specimen within crease-in ratio. So we will be looking at the indication of ductility using the software. Secondly, we will be comparing its strength with steel reinforcement. So as you can see, these are the two very important points that we would like to achieve in our project. And that is firstly, looking at the ductility or brittleness of the specimen, and second is comparing the performance with steel. Okay, this will directly indicate if steel can replace steel, if densified biomaterials rather can replace steel as a reinforcement material, therefore proving or disproving our thesis. Okay, we will conduct one set of 4 trials on each reinforcement material. So there are 4 materials in our methods, and that is depicted in this diagram on the right, and that is D16 is our 16 mm rods, and V15 is typically our 15 by 15 vesi and densified vesi, and P15 is typically our densified pine, which is going to be a 15 by 15 dimension, and B15 is going to be our densified bamboo at 15 by 15 mm as well. Okay, so we have 4 materials, and that means we will have 4 sets because we have 4 materials, and each of these materials will have 4 trials, and in each trial we will have 1 more longitudinal reinforcement bar than the previous. Okay, so we will be starting our reinforcement testing with 5 longitudinal reinforced bars, and in the next trial we will have 6 and then 7 and so on. Okay, until we have 4 trials. Okay, so the dimensions of the real bars, as I've already said, so it will be densified vesi, which is a 15 mm by 15 mm square Schrimber, and the Fijian, and this is densified vesi is Fijian hardwood. Its scientific name is Insia bijunga, and the next is densified pine, which is a 15 by 15 mm as well, which I've already said. And this is what we will be using is Fiji pine. We will not be using the treated pine. We will be densifying green pine, and the scientific name of this green pine is Pinus carbea. And next we will be using densified bamboo. Again, we will be using densified. We will be using bamboo that is native to the Fijian islands, and that is the Bambusa vulgaris. We will be testing these in our project. So moving on. We will have steel reinforcement as our control. Okay, as you know, we will be comparing all of the densified biomaterials with steel. Okay, for the flexural test, we'll have the same goals and dimensions of our reinforcement material with the previous test that I have mentioned. The only change will be the depth of the beam. So in our previous slide, we saw that the depth of the beam was 250 mm. In this, the depth of the column was 250 mm. In this, the depth will be 300. Okay, and also there will be a change in the orientation. In this, we had forces coming in from the ends of these columns. Over here, we will be applying the loads on the sides, typically as the loads will be applied to the beam. Okay, so let's move on. The second change that we will see is that we will only be testing for the tensile bars. Okay, so as you are applying pressure from the top, this top part will have this top half of this beam will have compressive force, and the bottom will be tensile. Okay, so the beams that will be applied at the bottom will be tensile beams, to put it simply. Okay, we know that concrete already has excellent compressive properties, but we're interested in the tensile bars only. Okay, for that, each trial will begin with 2 reinforcements, and then we will increase those accordingly. Okay, so moving on, the tensile strength of the test. Okay, tensile test will have the same the tensile test will have the same setup as the compressive test. Everything will be the same. We will have to determine the ductility or the brittleness, and we will compare the performance with steel. We will have the same testing systems, the trials and the sets. We'll have the same dimensions for the reinforcement. The only difference in this test will be the orientation of the force applied. As you know, that in compressive test there was forces coming in, and in the tensile strength test we will have forces leading out. Okay, so that will be the sole difference of the tensile strength test with the compressive test. And lastly, we will study the cracking behavior on ETABS, and this will be a major tool of analysis in our project. Okay, so we will have one specialized person, as I've explained already. We'll have one specialized person study the cracking behavior of concrete. Okay, so next we will use the color coding feature in Abacus for studying the cracking behavior. As I've already mentioned, blue zones normally indicate the low stress levels, and yellow, orange, and red usually indicate higher stress levels. Okay, so in that respect, the red zones turning blue increase that there is a release in energy. This usually is in the form of cracking. We will be looking for those indications, and the main goal in this study is to find any improvements in the cracking behavior with the increase in reinforcement ratio. Okay, and the second is to find any indications of ductility or brittleness in all test materials. Okay, from these 4 tests we can expect these results, and the first is that the increase in percentage of the reinforcement in all specimen will increase the ductility. The second is we can expect densified bamboo or densified biomaterials reinforced concrete specimen will to be as strong as steel. Okay, so the one thing that we would be focusing on, and we will already be expecting to be as strong as steel, is the densified bamboo reinforced concrete specimen. Okay, so we will be expecting that to be as strong as steel. We can now also calculate the amount of money you can save by buying densified bamboo instead of steel, or we can now say which material is cheaper in terms of strength. Okay, cost per strength ratio. So we will be comparing the cost and the strength ratio. We will see which material is cheaper in this regard. Typically, we predict that the densified biomaterials will be cheaper than the steel reinforcement. Okay. We can expect more tests on this subject to have densified biomaterials codified for the public to use. Okay, so we will have to have more research in order for us to develop equations or develop relationships between the reinforcements with the concrete. So we will have to have more tests on this regard. Okay, so this thesis is just a touch on the surface for predicting the viability of replacing steel with densified biomaterials. Okay, so this has been an overview of what the project will do. In part 2 of this video, we will present on the project management side of this video, of this research rather. Okay, so meet you in the next part.